Everybody, we're going to talk about distributions of variables and more particularly about properties of distributions and how we can measure them. So before we get into this, I do want to apologize to previous watchers because I've been recording stuff on my Keynote software for these things, and apparently it wasn't showing the pointer. So now I'm using a different recording technology so you can actually see what I'm pointing at. My bad. So before we get into today, I want to give you a little bit of sections of reading. These are sections that are in the Bishop book, and there are equivalent topics covered in the Hastie-Tibshirani book, The Elements of Statistical Learning. Again, the Hastie book is way more classic statistics. The Bishop book is a lot more Bayes focused, and you can find information in slightly different ways in both. So let's remind ourselves, we talked about this last time, about the idea of expectation. This is the average value of a function f, right? When we have a probability distribution of those x's that feed into the f function. So when some x's are more likely than other x's, what we end up with is merely a weighted sum of the functional values by the probability of the inputs. And this is, a weighted average. This is literally the mean of a distribution that you're used to. So this is clear. We've already talked about this, but the same framework can get us to other statistical parameters. And that's what we need to cover right now. So mean is just one possibility of a parameter. Besides that measure of central tendency, we may also be interested in measures of variability. How spread is the distribution? The classic measurement of that is variance, which is, if you don't remember, standard deviation squared. Well, what is variance? Variance is the difference between any given measurement x and the mean of the distribution squared. It's the squared distance between each data point and the mean of the distribution. Or to put it in discrete summation notation, for every data point, that's what we're summing over there, right? We have this form. It's the expectation, it's the average distance between the mean and each data point. So again, the mean, each data point, the mean of these deviations is the big E, and that's squared. So the variance is the expected or mean value of the distance between each data point and the mean. So for things that are very, very spread out, like if the distribution is very wide, if this is the x-axis, the average deviation is quite big. And if the distribution is very narrow around the mean, then the average distance is quite small. And that's how you should read this expectation. So you can write these in continuous or discrete ways. So we can also transform this definitional value into other forms. So I tell you that this expectation of the distance squared can actually be also written as expectation of the data squared minus the expectation of the data square the expectation. How can we see that? Well, we start with the definitional version, and we can merely factorize that square, right? After factorizing the square, you can FOIL and break it down and see that the two terms here and here cancel each other out. So you can also write this in other forms. Variance is the form where we say that if we only have like a univariate, one-dimensional distribution, or if all the directions in a multidimensional distribution have the same, right? That's a spherical variance. But in general, for multidimensional cases where our x is not a single variable, but it's a vector, we can write the same thing, but we have to write it in vector notation, where we have x vectors. And because these things are vectors, well, when we do multiplications, we need transforms to make sure that the size of our linear algebra outputs is the correct size. I refer you to your class on linear algebra for that one. All right. So these are tools, right? I've had some questions overall in like after class kind of situations where people are like, why are we learning this? What is this in aid of? Trust me, these Lego bricks are going to start to get put together in different ways to actually do machine learning, right? But in the meantime, here's another Lego brick. We oftentimes use logarithmic transforms of data. The logarithm is a very powerful tool because it lets us take things that had been multiplications inside a logarithm before we applied the log, and we break them out into additions outside, or powers become multiplications, right? So these properties of logarithms enable us to simplify calculations dramatically. We typically measure information theoretic things about random variables. Information theory is the study of, hey, when I know the roll of the dice, what information do I gain about those dice? For every bit of sample I get out of my random variables, I'm learning something about the process that generated that random variable. And so information theoretic tools often use logarithms, which is what we're about to do. And of course, logarithms can come in multiple bases. You can have a log 2, or a natural log, log to the e, or a log 10. We're almost always using log 2 because then our information theoretic measures, because they're log 2, are called bits. And it is exactly the same thing as bits and bytes, right? How many base 2 digits do I need to represent what I'm going to learn from this roll of the dice? If I get one bit of information, I need one base 2 digit to describe what I'm going to learn by the roll. And if I need, 3 bits of information, then I'm going to get 3 base 2 digits, right? Which is 2 to the 3rd power bits of information. All right, let's go on. So when we use measures to quantify information, we're usually talking about the so-called Shannon Information measure. So Shannon Information takes any discrete random variable, which has outcomes, right? Some sort of countable set of outcomes, by the way. You can't really do this for an infinite number of outcomes. So a roll of the dice could be 1 to 6, right? It's a finite set. So we roll dice, we get numbers out of them, and each number has got a probability of occurring. And probabilities are well formed, they all sum to 1, etc. So given all that, we can use the so-called Shannon Information measure, which, dun dun dun, is a logarithm of the probabilities. And in fact, it's either the logarithm of the inverse of the probability or equivalently the negative log of the probability itself. Let's think about this for a second, right? Probabilities exist between 0 and 1, right? So the log of a probability that's less than 1 and greater than 0 is going to fall in this negative territory. And what we're also going to get is probabilities close to 1, i.e. certain things that are very certain to occur. They don't give us any information. They get information close to 0, right? The log of 1 is 0. And so if something is certain to occur, if our coin is bent and it always turns up heads, each flip of the coin tells me nothing Before I flipped, I knew it was going to be heads because it was a bent coin. But if the coin is very uncertain, if it's fully 50-50 random, that's when I learn the most. Okay? So this information theoretic measure has zero information when stuff is certain, and large amounts of information when events are uncertain. Okay, using the coin example previously was maybe not the best one to talk about here because coins are binary. And if they are, anything off of 50-50, they're certain, right? If it's a 10% heads, that's 90% tails. So it's very certain what the outcome is. And if it's 90% heads, it's 10% tails. It's still very certain what the information outcome is. Okay, we're going to return to that in a minute. I thought that was my next slide. But let's talk about observing not just one die roll or one coin flip right now, but let's talk about what happens when we observe a sequence of them. Well, in regular probability land, if everything is conditionally independent, if every roll of the dice is independent of the next roll of the dice, those probabilities multiply. But thanks to the magic of logarithms, we can just add up the log probabilities, right? What had been multiplicative inside is now additive after the log. And so we can just add up the information gain from roll of the dice 1 with roll of the dice 2 and roll of the dice 3. Okay, so when we observe the same variable over and over and over again, right, information of each flip of the coin or each roll of the die, well, that was the information theoretic measure, right? Just to go backwards, that's log of the probability of the event. Okay, so, hey, what we might want to know is, on average, over many draws from this random variable, over many flips of the coin or many rolls of the dice, what kind of information am I getting on average? Remember, when it's a 50-50 coin, we don't know whether it's going to come down heads or tails. But if it's 90-10 either direction, well, we're pretty certain what the outcome is before we make the sample. So in the long run, the expectation of an information theoretic measure, well, expectation we know is just the probability times the actual value coming out of the function. And remember, the value coming out of the function is log probability because that's what I is. So this is called information entropy. Entropy, by the way, is exactly analogous, both mathematically and conceptually, with the thermodynamic idea of entropy, if you're familiar with your physics classes, right? But this is entropy of information. You can think of it just like entropy in physics as a measure of disorder. A high entropy system means the system is very disordered. A very predictable system has low entropy. It's highly ordered. I know what the outcome of the sample is likely to be before the sample is made. Okay, so as a binary variable coin flip, 0 or 1, what we can say is, here is the shape of entropy as the value of the Bernoulli variable, or binomial if we're talking about sequences, goes from 0, always tails, to maximally uncertain, 50-50 coin, to 1, full heads. Entropy is low at the certain sides and high in the middle where we don't know what's going to happen. Now, other things that are going to take place, we could look at just adding up the entropy of any set of outcomes. They don't have to be binary variables. What if their horse is winning a race and each horse is handicapped differently? Well, what's the total odds of a horse winning, right? So is laid out by these odds, right? And they have to add up to 1. These are probabilities. That's how the bookies do it, I guess. So if we want to know the entropy of this horse race, like how surprising will it be when we find the outcome of the race? Well, this is 2 bits of surprise. Every time we run the race with these horses, we gain 2 bits of information in seeing the outcome. It's 2 bits of surprise dealt with. If one of these horses was way more likely to win than the others, right, we get a lower entropy. But if every horse is exactly the same odds of winning, then we have higher entropy, maximum uncertainty. This is a less uncertain field than the equal field. Okay, and we can do this for other kinds of distributions. So the last thing we want to talk about is the idea of differential entropy. Entropy can generalize to many kinds of random variables. And we can do this and look at the difference between one variable and another by integrating over the random variables of a PDF. Okay? So this is our form for dealing with any kind of continuous version of this. All right. Lastly, we can use the idea of entropy as a measure of difference between 2 measured variables. So when we compare 2 probability distributions, we have 2 samples empirically of data, and we want to know, hey, how different are they from each other? We can use an information theoretic measure called the Kullback-Leibler divergence, or KL distance, also sometimes called relative entropy, right? And we read this as the distance between P and Q, distributions P and Q. So it's the expected value of the log ratio between the distributions. So this is an information theoretic measure. It's entropy again. But instead of just entropy, right, it's probability of the samples, right, log ratio between the distributions. So let's say we have, for instance, in this thing, 2 dice. We have a set of dice that we know are fair, and we have a set of dice that we suspect might be bent. And if we have a sample of fair dice, sometimes by chance we get, not as many 3s as we might expect, but life is like that. How different is Q from the possibly bent dice from the fair dice? So the thing about KL divergence is that it provides that measure, but it is not a proper metric. It is not associative. The KL divergence between P and Q is in general not the same as the divergence between Q and P. It's not symmetric. Okay? So that is an important thing to keep in mind. KL divergence is 0 if the 2 distributions are the same. Right? But they're not in general equal. So you can, of course, generalize this to the continuous case. All right, that's as far as we're going to go today. I will talk with you in lecture. Bye for now. And again, remember, we are actually going to start to use these tools to do stuff.